Good morning, ladies and gentlemen. My name is Martin Wagner from MicroPro. I would like to present and talk about this microbiological characterization. We have heard some words about that. This work was the results were obtained as a third work package of this Hystories project, which was about these microbiological aspects of underground hydrogen storage. After a brief overview, of the work, I would like to present the results on the microbial characterization, formation water samples from the porous structures we have investigated. In the second part, I explain our simulation experiments on the microbial hydrogen utilization. And finally, I discuss the microbial impacts of the underground storage of hydrogen and the ways to assess the risks. The objective, just briefly an overview, the objective of our microbiological work package was the characterization of microbial processes and the risks associated with the hydrogen storage in porous underground storages. For this microbial investigation program, deep samples were taken from numerous underground reservoirs and examined for the microbial colonization as part of the laboratory test program. In addition, simulation tests under increased pressure and real reservoir conditions were carried out with these samples to determine the stimulation potential of hydrogen. And based on these laboratory tests, guidelines for the risk assessment of the reservoirs for hydrogen storage were developed. Another task was to develop measures to control microbial activities. In order to assess the microbial risk that hydrogen storage can imply, we first looked at the microorganisms that might be involved in this process. As you all know, hydrogen is a very excellent energy source for numerous microorganisms, and unlike methane, it's also rapidly converted under anaerobic conditions by these hydrogen-trophic microorganisms. We already know very well which processes are based on hydrogen can take place in these subsurface structures. These four processes of sulfate reduction, methanogenesis, acetogenesis, and less relevant, the iron reduction, take place. These compete for hydrogen. And depending on which process dominates in each individual case, the corresponding product or a mixture is generated. On top of that, it should be noted that for long-term operation of these storage facilities, not only the primary hydrogen-consuming organisms should be considered. In the long term, also secondary processes based on the utilization of generated organic substances can also lead to technical problems. Since hydrogen can only serve as an energy source for the microorganisms, some other components as carbon sources and electron acceptors must be available in the liquid phase. Calcite, dolomite, siderite are common minerals of the rock matrix that can release carbonates and other ions when dissolved. These dissolved carbonate can then be converted by the hydrogen-consuming microorganisms. The situation is very similar with sulfatic and sulfidic minerals such as anhydrite and pyrite. The experiments show that in combination with a carbon source, such as CO2 or carbonate, the development of a complex microorganism population is often not only possible, but very likely. But now the question is, are the hydrogen-utilizing microorganisms present in the reservoir, and can they survive there? As part of the Hystories project, we were able to examine 11 deep formation water samples from 9 different gas reservoirs for the abundance and composition of the microbial populations. These diagrams show some results of our molecular biological analysis targeting the 4 major groups of hydrogen-consuming microorganisms. By qPCR methods, we quantified the copy numbers of their specific target genes, and the results show that the proportion of the major hydrogen-consuming microorganisms varies significantly between the different formation water samples. In 7 formation water samples, all 4 major hydrogen-related gene markers were detected. and 3 samples contain only low cell numbers, but at least one hydrogen-consuming group is almost always present. The results of the molecular biological analysis reveal the risk potentially caused by these hydrogen-related microorganisms. In parallel to this culture-independent analysis, the enrichment of viable microorganisms in the formation water samples was also carried out. For this purpose, very selective growth media were applied under strictly anaerobic conditions, in which the salinity and temperature were applied to the original sample conditions. Depending on salinity and temperature and the initial cell content in the samples, the cultivation required up to 12 weeks. Besides the hydrogen oxidizing groups, formation water samples were also analyzed for various other physiological microorganism groups, for instance, hydrocarbon oxidizing bacteria or acid producing microorganisms. This table only shows the hydrogen oxidizing groups. It shows that 11 from these 11 analyzed samples, 6 are massively contaminated with hydrogen oxidizing microorganisms. Another 4 samples contained microorganisms with lower cell numbers or activities. The enrichment cultures reveal 3 things. The living microorganisms are present in many formation water samples. An injection of hydrogen will activate these organisms if the living conditions in the storage allow it. And as a consequence, products like H2S, acetate or methane can be generated. A low growth rate or a low initial cell content should not mislead one about the later technical risk. Due to the huge dimensions of a reservoir, even slow-growing organisms can cause considerable problems in the future. What hydrogen turnover rate should we expect now? In order to estimate the possible effects of microbial hydrogen consumption, the hydrogen consumption tests were carried out under slightly increased pressure up to 3 bar and under real storage pressure in autoclave units. The experiments were inoculated with enrichment cultures from the original storage samples to achieve measurable hydrogen conversion rates in the time available. At the end of this cultivation period, the gas phase, liquid phase were analyzed for changes in the chemical composition. And also the microorganisms were analyzed by molecular biology. Various hydrogen consumption tests were carried out to study the influence of different parameters such as the type of carbonate, salinity, sulfate content, or pH value. These diagrams show the hydrogen consumption of 2 parallel approaches with simultaneous methane formation. The formation water was collected from a storage with a salinity of 2.8 sodium chloride and 40 degrees. Sodium hydrocarbonate served as an artificial carbon source. To clarify whether natural carbonate source of the reservoir rock can also be used by the microorganisms, the same experiment was carried out with the original core material. The diagram clearly shows that the carbonate of the rock can also be used to the same extent. After the incubation time of 47 days, we found that beside methane, acetate has also been generated in all cultures. Molecular biological analysis reveal that although the methanogens was a dominant group in the enrichment culture, also acetogens and even SRP were present in lower quantities. The microbial composition changed only marginally during the incubation time. With the same enrichment culture, high-pressure tests were carried out at 35 bars. A pressure drop could be recorded in all variants, in the pure core test, in the carbonate test, or in the mixture of both. Under all 3 test conditions, hydrogen was converted to methane. The highest hydrogen conversion rate was observed in the high-pressure test during the first 14 days, with a maximum rate of 0.4 millimole per hour. The consumption rate in the low-pressure tests were in the same range, but only at 0.2 millimole per hour. The question now is, How transferable are these individual measurements to other reservoirs? I would like to show you another example. We all know very well that there are some key parameters that influence the direction and intensity of the microbial activities or significantly inhibit them. The salinity of the formation water differs considerably from one reservoir to the other. Increasing sodium chloride concentration requires specific strategy of the microorganisms to maintain the osmotic balance of the bacterial cell. Saturated brine can only be colonized by extremely halophilic organisms. In our experiments, we found that significant methane formation only occurs up to a salinity of 120 gram per liter and was no longer detectable in any culture at around 150 gram per liter. In contrast, sulfate-reducing microorganisms show a significantly higher tolerance to high salinities and can even grow and convert in saturated brine. However, activity and conversion rates are correspondingly low. That means that the conversion rates strongly depend on the respective storage condition and the composition of the microbial population. In addition, microbial populations and geologic structures are, as in general, do not occur as pure cultures. We must therefore anticipate different metabolic pathways simultaneously. Therefore, it's almost impossible to make generalized statements about the conversion rates from lab experiments. Nevertheless, we determined maximum conversion rates for the sulfate-reducing microorganisms of up to 500 millimole per hour and up to 27 millimole per hour for methanogens. In the literature, values up to 900 millimole per hour can be found. But again, these values depend strongly on the respective reservoir conditions and have to be determined specifically for each individual case. But what are the possible consequences of the microbial hydrogen utilization, and how can we assess and describe the risk for the individual underground storage? We just heard about the impact of the H2S production, or H2S in general. Let us briefly look at the technical damage potentially caused by the microorganisms. Basically, any microbial activity is detrimental to the operation of a porous underground storage. While the loss of hydrogen might be economically of minor importance, the formation of H2S by SRP or plugging by bio-based solids and biofilms can cause major technical problems in porous structures. As we have seen, sulfate-reducing microorganisms can develop quite well in subsurface formation even under extreme conditions and have particularly negative effects through the formation of H2S. For these reasons, special attention must be paid to this microbial group. When we talk about mitigation strategies, we first think in most cases of biocides. However, the use of biocide has some elementary disadvantages. For each substance, there is a minimum effective concentration, which needs to or can be determined in the lab using test cultures. Here we must distinguish between the killing and the inhibiting effects. If the concentration falls below the necessary concentration, for instance, due to dilution in an open system, the biocide become ineffective. This dilution effect always inevitably occurs in porous structures in a certain distance from the injection well. If the biocide become ineffective, many biocide products can be degraded by the microorganisms or even serve as nutrients. Unfortunately, fluids in porous structures do often not disperse as expected, and it's difficult to ensure an equal and effective biocide concentration. In order to determine the effective biocide concentration under reservoir conditions, we run tests with enrichment cultures of SRP and methanogens in many different salinities. These examples show triplicate SRP cultures with increasing biocide concentrations. The tests were cultivated for up to 12 weeks. At 0.1 and 15% salinity, the activity of all test cultures was completely inhibited by a biocide concentration of 50 ppm. But in saturated brine, 2 biocides required concentration of up to 200 ppm to inhibit the microbial activity. That shows that we have to test it and not just only take the data from the manufacturer of the biocides. With these biocide tests, the lowest effective concentration can be determined very precisely. What is difficult, however, is the homogeneous application within the reservoir. An alternative to biocides is the exploitation, or might be the exploitation and shifting of natural parameter limits. Of course, only very few conditions of a deposit can be influenced at all in the long term. But some structures already reach threshold parameters that can be used to slow down the microbial activity. This includes, for instance, low sulfate content or carbonate concentration or a high pH value. We have studied the impact of several parameters to evaluate whether a modification could be useful to suppress microbial activity. The tests with increasing pH values show that at a pH of 10 or even higher leads to a significant reduction of microbial activity. A possible application in practice naturally requires the study of the chemical and technical consequences of such a modified pH value. The analysis of formation water samples showed that the reservoir with temperature up to 80 degrees often contain active microorganisms. An interesting aspect in this connection is the connection between salinity and temperature, as both stress factors reinforce each other. This effect is already known from oil reservoirs. The diagram summarizes published limits of microbial enrichment cultures from oil and gas reservoirs and some subsurface structures. A very similar summary was recently published by Tyson. These data, as well as our own results, suggest that there is a range of medium temperature and salinity where microbial activity is strongly limited. Since gas storages often contain increased salinities in the formation water, this correlation can be used in the microbial assessment of the suitability of hydrogen storage. Within the Hystories project, almost 500 hydrocarbon traps were evaluated in this context. On this basis, we can already assign a very basic risk ranking for potential storage site with a high, medium, and low risk. This allows an initial risk assessment to be made at a very early stage of the planning. As you can see, there is a substantial number of traps which can be classified as low risk site. For the other traps, further parameters have to be taken into account to assess the risk in more detail, of course. For an initial basic risk assessment, from our point of view, it's not necessary to determine all storage parameters in detail. Some storage parameters that do not limit the microbial activity are of secondary importance for the initial risk assessment. We have found that four key parameters are crucial for the initial evaluation of an underground storage: temperature, salinity, sulfate content, and the availability of a carbon source. The advantage of this selection is that for many geologic structures, this information is already available. On the basis of these four parameters, we have created a very simple risk chart that can be used to make an initial classification. With this chart, it's possible to, at a very early stage of the planning, to rank potential storage sites and focus on low-risk sites. A combination of high temperature and salinity together with low carbon and sulfate content minimizes the risk of a microbial activity. At a later stage, a more detailed microbial assessment must be carried out in any case. Overall, these results of the research with real formation water samples clearly show that, in contrast to methane, hydrogen storage requires a detailed study of the site-specific parameters on microbial stimulation potential. This is important for selection of a storage site or to minimize the risk during the operation. That's it from my side. I would like to thank you, all the project partners of the Hystories project, for this excellent cooperation, and of course for the financial support within this project and research program. Thank you.
We have 15 minutes for questions.
I have a question about your test. You used artificial consortia of microorganisms, or the same microorganism you found in samples?
Yeah, the second. We
The second,
enriched
okay.
samples from the.
And did you add, and second question, did you add any micronutrients in order to awake the basal metabolism of microorganism, or they start to consume hydrogen and carbon salts by themselves without any addition?
The media we used is two things. Either a artificial growth media, which includes all the micronutrients, but no carbon source or energy source. So these are pure mineral medium without any additional, like when we investigate, for instance, the consumption of CO2 and H2. Then we only use these components as a energy and carbon source, and no other nutrients.
But do you think without the growth medium, do you think they will be able anyway to consume hydrogen and carbon source?
Yes, because we did also the second thing. We used the original brine or original formation water as a culture medium, and just apply this hydrogen or a combination of hydrogen and CO2 to this medium.
Okay.
So we use the original formation water, original core, and the enrichment from this site to do these, for instance, these high pressure tests.
Okay. Thank you. Thank you very much.
Another question?
So a few questions from the chat. Starting with, was there any relationship between formation water pH and type of bacteria population? And then were methanogenes found in samples from depleted gas reservoirs?
Sorry, I didn't get the first part.
So first question was there any relationship between the formation water pH and the type of bacteria population?
Difficult question. The formation water or the pH of the formation water samples was not that different from each reservoir to the other, when I correctly remember. And there was no clear correlation between the pH and the microbial community, as far as I know.
And then the second part was, were methanogenes found in samples from depleted gas reservoirs?
Yes.
Yeah. Maybe I've got another one. So what is the lowest reservoir temperature that we think hydrogen-consuming microbes cannot survive? And the second part is, since we know that above approximately 125 C, no microbes should live, but what is the upper temperature limit for hydrogen-consuming microbes?
Yeah, there is no lower limit, because you can think of 20 degrees reservoir temperature. That's not a limit for the microorganisms to grow. So there is no lower limit, and the upper limit clearly also depends, beside the temperature, also on other parameters. As I explained, salinity, for instance, the 125 degrees as an upper limit is mainly for laboratory tests. We have seen that a lot of reservoirs with a temperature up to 80 or even 90 degree contain active microorganisms in low quantities, but still alive. So, of course, from the technical point of view, these are very extreme conditions for the microorganisms and will probably not allow a very active and substantial consumption of hydrogen. So I would rather, from my experience, have a limit, or let's say a limit of substantial conversion rates of, let's say, 80 degrees. Higher temperatures will probably cause a lot of problems for the microorganisms to have substantial conversion rates.
Hi. In storage operations, you would pressure cycle very quickly between high pressure, very high pressure, and low pressure, and then vice versa. What do you think the impact of a very fast pressure change would be on the microbial population?
I'm not a technician, but I would expect that the pressure change within the reservoir would not cause any problems for the microorganisms. There is methods to crack the bacterial cell by a very fast pressure change, but this is probably not the same pressure change we talk when we think on technical reservoirs. Maybe we discuss it later, but the pressure is actually for the bacteria not a very critical thing within the range of, let's say, 200 or 300 bars. Up to that pressure, it's more a chemical or physical influence on the bacteria, not the physical pressure.
No other question?
In the context of cycling with biocide, how long does it take for this conversion? What's the speed of conversion? If you're cycling, if you're refilling a reservoir every 90 days, and you're putting in a lot of methanol-based biocide or something, how long before the bacteria accumulates to a sufficient, or the biological conversion gets to a significant rate?
The population itself, the bacterial population will develop and will stay there in the reservoir and do not change even once it is established. Whether there is a cycle change, it will not influence the bacterial population very much, but the activity might be different. So the bacteria may starve, may survive for a while, but if they are supplied with hydrogen during this injection, then they will start to convert the hydrogen. The conversion rates, as I mentioned, is very dependent on the conditions in the reservoir, and it's very difficult to give a prognosis without any background information.
So are you saying you can suppress biocide? Can't eliminate?
With the biocide, you can suppress, of course, you can suppress bacteria by biocide. You can test it, you can apply it, and within a certain range, it will work for sure. As long as the concentration of the biocide and the contact time is sufficient enough to kill the bacteria or to suppress the bacteria. What I would like to highlight is that there is a zone beyond this working concentration where the bacteria can still survive and maybe also adapt to this biocide concentration if it is not high enough to kill them. And this might be may cause a change of the population more to the adapted bacteria in the long run. So you may change the biocide over the time, and there is different strategies also for that, of course.
Last question.
Did you find any case of cross metabolism? For example, some sulfate reducing bacteria that are able to eat volatile fatty acids.
Yeah, definitely. That's a point I wanted to mention, is that beside these direct hydrogen using bacteria, there is other groups which are waiting for the products of this first
and they can grow.
That's exactly the point. So with a supply of hydrogen, if in the worst case with the supply of hydrogen, we activate a microbial community which can then cause secondary processes, and that would be critical from my point of view.
Thank you.
Thanks a lot, Martin.